I should say that this is actually a talk with the second half. The first half, I didn't realize it was clustering and wrote a slightly different talk. However, in my overlong response this morning, I sort of gave the substance of the last half of my talk. So let's proceed with this one. Okay, so an outline, just a lot of this will have been covered by many other speakers. Examples of unlabeled networks and generative models. Non-parametric models, which can be identified with graphons. Block models, which I will focus on with expected average degree lambda, not necessarily the model, but the graph as a whole. And asymptotics for three regimes. One, which is actually, in some sense, the easy regime, but also from a statistician's point of view, the most satisfying, which is when the degree goes to infinity faster than the logarithm of n, which means, in terms of Erdős-Rényi, that there are no isolated points. And that's true for all of these graphs. Then lambda going to infinity, but lambda equals big O of log n, and finally lambda equals big O of 1, which has been the domain of many skilled probabilists, with results which, again, from a statistician point of view, are not, unfortunately, intrinsically are not that satisfactory. Okay, so here's an example which you've all seen. This is the Facebook network for Caltech, 769 nodes, average degree 43, which is pretty high. You can't tell anything from this, but it looks pretty. Let me switch quickly to a mathematical formulation. You see what I'm more comfortable with. But there will be some more pictures. So the graph, as usual, I'm talking about an undirected graph. So in other words, you can't tell whether I like you or you like me. We both like each other, rather. Arbitrarily labeled vertices. A is the adjacency matrix, as usual, defines it. And I'll also use just one notation, which I guess hasn't been introduced, which is di for the degree of the ith vertex. And the implications, of course, of the mathematical description, again, I'm really, I think, preaching to the converted, so I'll go very quickly. Undirected means that relations to or from are not distinguished. Arbitrary labels means that individual and geographical information is not used, but can be used for validation. Of course, following up on this morning's conversation, you really do want to use the labels, and the validation ideally comes from the outside, as it usually does in clustering. Clustering is unsupervised learning, right? So there is no real definition of cluster apart from something that means something to somebody in another field. Okay, just mentioning quickly some very elementary descriptive statistics. The degree of the vertex, the average degree of the graph, the number and size of connected components, the geodesic distance, homophily, which measures sort of the concentration of the graph. It just a triangle means that if I like you and if A and B are connected and B and C are connected, then A and C are. And then there's a large paper of Leskovec, Lang, Dasgupta, and Mahoney, which has lots and lots of different measures for large graphs. These the first four are, of course, classical ones. Now, here's examples of networks, which I took from Leskovec et al., and which is basically plotting the number of nodes versus number of edges. And if you translate that in log-log scale, and if you translate that into plotting degree versus number of nodes, what you find is that essentially the degree grows, in these cases, as n to some small power. However, that could also mean log n, of course. But in other words, there is some message here that n does grow. I mean, the lambda, the degree grows with the number of nodes. I'm sorry?
Plus C.
Yes, indeed. Thank you. Of course. Okay, stochastic models. Again, we've heard many of those this morning. The Erdős-Renyi model, which is probably the oldest, goes back to the late 50s. And it enables you to think about probability distributions on graphs of n vertices, which is equivalent for unlabeled graphs to thinking about symmetric n by n matrices of zeros and ones. And Erdős-Renyi, slightly modified, place edges independently with probability lambda over n, where lambda is the average degree. N choose 2 Bruni trials. So you have n squared trials, and the probability is lambda over n, and lambda is the expected average degree. The statistical generalization of the Erdős-Renyi model, which was, again, has been mentioned before, but let me remind you, is the natural one to induce inhomogeneity, if you want, within these exchangeable graphs. So you have a community label, which you assume is multinomial. There are k possible communities or clusters or blocks, but we're not talking about population statistics. And the relation is that given the membership in the communities, the probability of an edge depends only on the membership of the 2 endpoints, and the edges are conditionally independent. So k equals 1 is the Erdős-Renyi model. So this model, again, Pat talked about, and as did Peter. Now, as has been mentioned, I'd like to go to a non-parametric asymptotic model, and you'll see why I call it asymptotic. I mean that the model itself is asymptotic. So we have latent variables, uniform 0, 1, associated with vertices 1 through n. You have a function which is symmetric, which goes from the unit square to 0, 1. And you have the graph probabilities are defined by the probability of an edge given all of the latent variables is depends again only on the endpoints, but is a function h of xi xj. And that's what I like to call a non-parametric model. Now, again, I'll mention again a property that Peter mentioned, that beautiful reason, if you want, for considering these from a mathematical point of view is that every probability which is on the infinite graph, which is invariant under permutations of the labels, is a mixture of certain p sub h's, which are, in fact, the ones that I defined. So h is the function which defines the probability of an edge given xi xj. So these p sub h's are all ergodic. So let me just go back, remind you, there's the p sub h. So this is really completely analogous, as again has been pointed out before, to the situation on the line. If you ask on the line, you have exchangeable random variables, then the joint distribution is always a mixture of IID sequences, and it's the IID sequences which are actually ergodic. And here, these things are also ergodic. They're not quite IID, but they're basically, there's little knowledge of what happens. If you don't have edges connecting you, then you have no information. This also coincides with the notion, again, that has been mentioned this morning, of the Lovász graphon. I'm not going to use that anymore, but I'll just assume this model, which has been called the exchangeable model, from now on. Now, as I think Peter mentioned, and also Pat, there is a problem with just leaving this function h fixed if you want to do asymptotics, because then you basically automatically have expected degree of order n, which is never observed, as you saw, for example, in the examples I gave and many others. And so what you do is you scale it down by a factor, and a natural factor is the probability of an edge that controls the density of the graph. And then, given that you have an edge, you can talk by Bayes' theorem about the conditional density of the two latent variables given that you have an edge. And that function doesn't depend on n. And that's the function we'll play with. The average degree is rho n times n minus 1, and that enables you to have the average degree range from big O1 to big O(n). Let's see. Warning? Thank you. Okay. Examples of models. Block models, which are where you have the H taking on a finite number of values. And these correspond exactly to the block models I believe were defined by previous speakers. You essentially have class, or I define them, you have classes, and then there's a probability of communicating, of having an edge, but now given the membership of your classes. So if you want the latent variable becomes discrete. There are only, you could just as well say that you have a latent variable which takes on the values 1 through k. It's been noted early on that block models do not have a property which has been noticed in practice a lot, which is that the degree distribution tends to resemble a power distribution. And Chung and Liu and others showed that, of course, by modifying this W sub n function, writing it as A of u, A of v times 1 over rho n, which permits, of course, the A now to be genuinely a density rather than a probability, you get whatever power law behavior you want by taking A of u 1 minus u to the minus alpha. And there's a model that I think most of you may have encountered, the so-called preferential attachment model, which has a nice interpretation that nodes enter sequentially and attaches to I and Gn with probability proportional to degree. And you can show that in a rather precise sense it's actually asymptotically completely equivalent to drawing from a graph with A equal to 1 minus, a constant times 1 minus u to the minus a half. So it has the power law property. And okay. All right, I'll switch very quickly now. I have worked on other methods of estimating. So now I'm going to focus on estimating parameters of blocks and, of course, identifying community members. And from a previous result by Ayu Chen and myself, we were able to do something which computationally was only marginally useful, but I think from a theoretical point is moderately useful, interesting, which is you can look at the data, you can look at the likelihood and ask how good is the likelihood, if you could compute it in a reasonable amount of time, in classifying, right? You can write down the likelihood of the block models. How good is it in classifying individuals in each of the classes? And it turns out, and I'll just jump over this, it turns out that because of this, and there's also something called the variational likelihood, which I think perhaps more of you are familiar with than I am, but this is computable reasonably quickly. And the result, which I'll quickly switch to, is that in this magic domain where lambda sub n over log n tends to infinity, essentially you asymptotically know the labels, know all of the labels. Right? So it isn't that your error rate goes to 0. It's that you actually have nailed down with probability tending to 1 all the labels. And because of that, you can easily conclude that indeed, yes, in this regime, maximum likelihood behaves as it should, as does variational likelihood, and they are the best methods of classifying. But anything actually in this regime is the best method of classifying because you're classifying perfectly with probability tending to 1. Okay, lambda tending to infinity I will go over very quickly because it'll be gone over in greater detail by other speakers. But there are many methods, as Jen mentioned: spectral clustering, pseudo-likelihood. These are all methods which are applied in applications to block models. And in all these cases, you can't, as soon as lambda goes to infinity more slowly than log n, you cannot nail everybody because there are isolated points, but you can drive the mistake rate to 0. This is something I haven't dwelt on, but as statisticians, one is somewhat interested in parameters of these models. Again, when you know, of course, the identity of the members, you can estimate perfectly, I mean, you can estimate the parameters at optimal rates as if you knew the labels, and that's well known. Here you can't anymore. And I believe, although I don't think it's been shown, that in fact, below lambda over log n tending to infinity, you cannot estimate the parameters at the same rates as if you knew the labels. Lambda equals big O1. There's been a great deal of work. Actually, I expect that Andrea will talk about it. No? Okay. But in any case, unfortunately, the best you can hope to do is this. That is, that the proportion of mistakes is bigger than a half. Thank you. So, okay.
Peter, I have a question.
Yes, ma'am.
So these are all under the assumption that the data is generated from the underlying block model, or?
That's correct. That's correct. That's correct. There are theorems which I don't know which can be written down, which say that if in fact the data isn't generated from the block model, it's going to look as if it were generated from a block model which is in some sense closest to your block model. Unfortunately, the sense is in terms of the Kuhlbach-Leibler metric, in terms of the infinite probability measures on the lattice. But there it is. And you can... Okay, this is something new, which I wanted to talk about. So I've been working with a postdoc, jointly of mine and Mike's, Purna Sarkar. And we asked, well, okay, so you have this block model. Let's assume that it holds. But we don't know what K is. Is there a way of choosing K in a more or less principled way, starting without knowing it? And we actually answered a somewhat simpler question, namely deciding whether K is 2 or 1. In other words, Erdős-Rényi or 2 blocks. But of course, in principle, that can be used with any method of clustering to choose when to stop, right? Because you start out by cutting once, and then you look at each of these guys, and then you decide whether to cut them. And what you get is actually a hierarchical method of clustering in that way. So, and we prove, thanks to the work of about 15 years of probabilists, that in fact, you can take the eigenvalue of the adjacency matrix minus its expectation as estimated, scaled as estimated, and show that if in fact it's a Erdős-Rényi model, this goes to Tracy-Whittem, but if it's not an Erdős-Rényi model, it blows up, of course. If there's more than one block, it blows up. Now, it turns out there's something amusing which was not quite expected, which I'll mention, which is that actually Tracy-Whittem in this case is not such a wonderful approximation. It's known that for Gaussian matrices, it's superb. But in this case, if you actually look at it, it isn't. But what can you do is you can do what's called the parametric bootstrap. You can take a small number of observations, right, from the postulated Erdős-Rényi model with the estimated P, estimate the mean and variance of the Tracy-Whittem distribution under that, plug it in, and you get much better fit. That's a trick that was discovered a long time ago by George Box, where he showed that scaling chi-squareds actually did better than chi-squared in approximating the log likelihood ratio, the 2 log lambda. Okay. All right. So here's just some examples actually applied to data, though not real data. But well, real data, yes. But no. This is a case where I guess Leskavec managed to get ground truth by manually labeling people. I think I'll make it. And he then had a method of clustering of his own, which was dynamic and which didn't involve an explicit stopping rule, and of course I'm showing this because it turns out that we did much better. According to this average measure of agreement with truth. This is something called the F measure, which is precision times recall times 2 divided by precision plus recall. And the white is the Tracy-Whittem as corrected, and the black is the Leskovec story. And then, just to give you a moment of honesty, we looked at this famous karate club thing where, in fact, truth is supposedly known, at least anecdotally, that there was a quarrel in the karate club and a certain fraction of the members went one way and another fraction of the members went the other way. And so this is what's called ground truth. And if you use a very small p-value on Tracy-Whittem, you get the truth using spectral clustering, actually, and at each stage. And then as the p-value increases, you cut off another clique. Now, whether that's meaningful or not, we don't know. We don't know much more about the history of the karate club than that it's split. So that's the story. Okay.
Questions?
Yes. So
Yes.
can you give a little bit more details about your result on testing k equals 1 versus k equals 2? So what do you assume?
Okay. What's assumed, we really, the test statistic is well defined.
Yes, that I understand.
Right, okay. And so now the question is, what's the null distribution that you apply the test to? You reject for large values of that test statistic. And the null distribution is Erdős-Rényi, because that's what it means to have one block, one homogeneous block. And the alternative, in some sense, suggests the form of the test statistic, but the test statistic isn't tied to a particular alternative.
But your result, I mean, saying that you are consistent for this test, you need to assume something on the alternative, that there is a gap between the probabilities.
Oh, of course. Oh, yeah. That's right. But did I say consistent? I think when I said consistent, it is consistent, yes, with appropriate conditions. I guess I was more amused in seeing that actually this method worked in a more complex situation, if you want. But yes, it surely is. If you have, I think, if the eigenvalue tends to infinity, if you have a two-block model, right? So you have consistency for any level.
If there is a constant gap between the probabilities, you can come up with simpler statistics.
Yes, you can. Well, can you?
I don't know.
The trouble is that the probabilities of these A's are really nasty things. They're sums over all possible permutations of the labels.
Yeah.
But you're quite right. You could probably use the variational, the variational likelihood for one block versus two blocks. That's correct. But whether that would do better in a general situation where, in fact, you don't believe there's a block model, but you're looking for inhomogeneity, that's less clear.